Okay. Good afternoon, everybody. Welcome to this new session of Th-LYR. This is a series of lectures in theoretical physics given by young researchers. Today, I have the pleasure to introduce the lecture by Duaso Pueyo. He's a PhD student and part of the Cosmology group at Amsterdam University. Is currently working on a new approach that explores the jitter and inflationary correlation functions from the point of view of time without time. This is called cosmological bootstrap. Today we'll talk about this approach, explaining its ideas and the physical interests in studying these objects. I remind you that the idea of these lectures is to have an informal environment where participants can ask questions and actively interact with the speaker. Therefore, if you have any questions, comments, or whatever, feel free to ask Carlo directly by switching on your microphones during the lecture. And I would ask you to activate also the video camera, just to have a contact with the speaker. And I want to thank Carlos for accepting our invitation to give this lecture, and I give the floor to Carlos.
Okay, thank you very much. So thanks for the introduction, and thank you also for inviting me to give these lectures and for thinking about me. Yeah, well, so you have introduced me already, so I don't need to introduce myself. But yeah, basically I'm a PhD student in the University of Amsterdam. And as Matteo said, please interrupt anytime if you have questions about what I am saying. I'll be happy to try to answer. Something else, well, I will be writing in real time, so I hope the pace is okay. It's not too fast or too slow. Just tell me if it is too fast or too slow. Yeah, well, I hope I calculated on a correct amount of stuff to tell you for the 4 hours of these lectures, and I didn't put too much or too few stuff. We will see. Okay, so let's start. I guess you can see my screen and you can see also the pointer. Yeah, perfect. Very good. So yeah, this talk is based on the work that I've been doing with my supervisor Daniel Baumann, and also with my other collaborators Wei-Ming Chen, Austin Joyce, Hayden Lee, and Guillermo Pimentel. And the main references for what I will be talking about are these ones. This is basically well, all of the work that my group have been doing on this topic of bootstrapping cosmological correlators. And then I have also added here a few other references for background that have to do with, you know, just inflation, computing inflationary non-Gaussianities, the CFT, the conformal bootstrap, etc. And of course, there are many other references and many other works, much more people working on this topic. I will be mentioning some of them in these lectures. Okay, so let me start with the outline. Basically, in these lectures, we will be learning about the cosmological bootstrap, as Matteo said. So I divided them in 3 parts, basically. In the first part, I will try to talk about, well, which cosmology are we trying to do, which observables are we worried about, what is it that we want to measure, etc. In part 2, I will try to explain what is a bootstrap. So actually, let me write it. What are cosmological correlators? That will be answered in part 1, hopefully. Actually, also, why do we care about them? In part 2, I will try to explain what is a bootstrap. and why do we want to bootstrap cosmological correlators. And finally, in part 3, I will focus in the technical details of this cosmological bootstrap. So part 3. Okay. So basically, I will try to explain how do we bootstrap cosmological correlators. What are the techniques? So basically, in parts 1 and 2, I will try to answer the questions of what and why, right? What are the things that we care about? What is a bootstrap, and why do we care about, etc.? Why do we want to do this? So basically, introduction to the framework and motivation. And then in part 3, I will try to answer the question of how. How are we going to do this? So what are the techniques? What are the methods? Very good. So let's start then with part 1. Yeah, I have my script here, so I will be looking a lot here. But okay, so let's start with trying to explain what are the observables that we care about and why. So this is a picture of the evolution of the universe, basically. So time flows in this direction, right? And this thing here is basically the universe today, what we see today in the sky. Here, a bit back in time, we have structure formation. So basically, the period of the universe in which structure like stars, galaxies, etc., form. And a bit further back in time, here, this is a depiction of the primordial plasma. So you know, back in time, there was a moment in the universe in which the universe was actually filled with a very hot plasma of charged particles and photons. Okay, so this plasma is this yellow thing here, and one nice thing about this plasma is that we can observe it kind of directly, because at some point the electrons and the protons that were flying around in this plasma combined. When the plasma cooled enough, they combined into neutral atoms, and then the photons could freely stream. And since then, they have been traveling, filling up the universe and traveling in all directions. And we can actually now measure them. This is what we call the cosmic microwave background, right? So CMB. So yeah, we have this window to the universe when it was just 380,000 years old. And in the same way, we can also, in a similar way, we can also observe these early stages of structure formation if we look far away enough, and so on. So, as you know, well, let me say also that this surface here that I depicted here in red is basically the beginning of this hot Big Bang, of this evolution of the universe, and I will talk in a moment about this. So, yeah, cosmology, of course, is not an experimental science in the same sense as the rest of physics. We cannot repeat the experiment of the creation of the universe. It only happened once. So what we do instead is we look at the structures that we can see, for example, the CMB or the galaxies today, and we try to measure correlations and patterns in these structures. So, for example, we can try to correlate 3 points in the distribution of galaxies today, 3 or 2 or 4 or whatever. For example, this would be a 4-point correlation. And by doing these correlations in the structure of the galaxies or in the cosmic microwave background radiation that arrives to our detectors, we can study the patterns that we find. Okay. So to be a bit more precise, maybe, for example, this 3-point correlation here in the distribution of galaxies could be a 3-point correlation on the density field, right? To have homogeneous density, we have variations over that density. For example, places where there is a galaxy halo, that those are very dense places. And we can try to study such a correlation function. In the case of the CMB, for example, this would be a correlation function on the temperature and isotropies. So, these photons that arrive to us on the cosmic microwave background, they have a temperature, but their temperature varies depending on the point of the sky that you're looking at. And you can try to characterize these variations by studying these correlation functions. Very good. So because we kind of understand well most of this of the evolution of the matter in the universe, we can trace back all of these correlations that we measure. And by tracing back, I mean we can evolve them back in time, so that we can relate this correlation here to a correlation on the primordial plasma, right? And we can trace them back all the way to the surface of the beginning of the hot Big Bang. And one thing that we realize is that these correlations here, these primordial correlations that seeded the structure formation and the rest of the correlations that we see in the late time structure, they are correlated over, there exist correlations over distances that in principle could not have been in causal contact, because there was not enough time right in the beginning for them to be in causal contact. But however, they are correlated. So that is how we know that there should be a period of primordial in the primordial universe, a primordial period before, let's say, the beginning of the hot Big Bang, that in such a way that some causal physics could give rise to these correlations. And this is what, well, in general, what people have been working with is with a period of accelerated expansion that we call inflation. Right? And this surface here, which is the surface of the end of inflation, beginning of the classical Big Bang evolution, is called reheating surface. Very good. So I said that all of these correlations, we can trace them back to this reheating surface. And the reason why, well, the reason why we say that these correlations are the seeds for the subsequent evolution is because inflation was a very energetic process, and in this process, well, there were quantum fluctuations in the background, and these quantum fluctuations in the end of inflation, in this reheating surface, translated into some fluctuations in the density, for example, something like this. And these fluctuations in the density seeded the structure. So, for example, they gave rise to fluctuations in the density of this plasma, the density of photons and particles in the plasma, that later on evolved into density fluctuations in the distribution of the structure, and so on. So these fluctuations here, these primordial fluctuations, are the seed for the subsequent formation of structure, and their correlations characterize are the initial conditions, let's say, for the other correlations that we measure in the universe. So this means that from the observation of these correlators in the late time structure, we can infer them. And this means that we can also learn from inflation from this correlation. So these are the objects of interest, okay? Correlation functions in this reheating surface. Okay, and I've mentioned that they are important because they are the initial conditions for the subsequent evolution, but they also contain information about the dynamics of inflation. So the dynamics of inflation is encoded in this primordial correlation. Okay. So here, I have rotated the picture that I had before. So this is inflation. This surface here is the reheating surface where inflation ends, and the perturbations, as I explained, they come from quantum fluctuations in the inflationary spacetime that then are. So, for example, here here we have some particle production, okay, in the inflationary spacetime. Two particles are spontaneously created, and then the expansion of the universe during inflation drags them away from each other in such a way that in the end, in the surface of the end of inflation, we're going to have some correlation in the fluctuations that they give rise to. In this other example here, I have pictured some particle production, and then these particles stretch away also, and they decay into other particles, which also generate some correlations in the fluctuations at the end of inflation. So, we're going to have information. This decay, of course, happens because there is some coupling between the particles. So all of that information about these couplings that gives rise to these decays and so on is going to be encoded in these correlations. So that is why these are so interesting objects. Here, by the way, I'm using eta, which is conformal time, and the surface of reheating we will, by choice we will put it at eta equals 0. Okay. One reason why this is very important is because inflation was a very, very energetic process. Okay, so just for comparison, the LHC reaches energies of 10 to the 4 GeV, so around 10 electron volts. However, inflation was much more energetic than this. It could be, well, we don't actually know the exact scale of energy that drove inflation, but it could be as high as 10 to the 14 GeV. It could be as high as 10 orders of magnitude above the most powerful particle collider that we have on Earth. So this means that in a way, inflation, the early universe, was huge cosmological collider. Because in the same way that in a particle collider we can, scatter particles against each other and measure what happens, measure the interactions and so on. From the study of these correlations, we can also infer the dynamics of inflation, which took place at a very, very high energy scale. Okay. Any questions so far? If not, let me continue. So, as I said, the observables of interest are correlation functions at the end of inflation. So, in order to be a bit more precise, so correlation functions of what exactly, right? So I should mention that there are 2 degrees of freedom in every inflationary model. a scalar one that is usually called zeta. It's just this zeta is just a gauge invariant combination of scalar degrees of freedom coming from the inflaton, which is the scalar field that drives inflation, and the graviton. And on the other hand, we have a tensor degree of freedom, which is basically the traceless transverse part of the graviton. Okay, so these are basically the two most important degrees of freedom of an inflationary model, and it is the correlation functions of these degrees of freedom that we will mainly be focusing on, or the ones that are observationally important. So which kind of correlation functions are we interested in? So for example, 2-point functions. These are the simplest. And well, one is the 2-point function of the scalar, the scalar curvature perturbations. And this one has been measured. I will talk about it a little bit later, but this one we have measured from the CMB. And another 2-point function that we could try to infer from the observation is the 2-point function of the tensor modes, and this one has not been measured so far. And this one, well, now there are some experiments that are trying to measure and that will try to measure it. But it is important because from measuring it, we can tell the energy scale of inflation. It's actually contained in the size of this 2-point function of tensor perturbation. So these are the 2-point functions, but of course we could also measure 3, 4, etc. So higher point functions. And this is what we call non-Gaussianity. Okay. It's because if we are drawing these correlations from a Gaussian distribution, then we just need to know the 2-point function. The rest of n-point functions are characterized are given in terms of the 2-point function. But if the distribution is non-Gaussian, then we need information about the others generically. So that is why these other higher order n-point functions are called non-Gaussianity. And this also has not been measured. And these are, well, really, these are very important because, well, I'm thinking, of course, about correlation functions like the correlation of three scalars, or I don't know, graviton and 2 scalars, 3 gravitons or 4 scalars. This kind of correlation functions, and these are important because they contain the information about the dynamics. Okay. And this is easy to understand. It's similar to the case of scattering amplitudes. If I give you a 2-point scattering amplitude, that's just a propagator. That doesn't tell us anything about the dynamics, about the interactions. That only tells us something about the free theory. If you want to characterize the interactions of your Lagrangian, then you have to give me the 3-point scattering amplitude or 4-point scattering amplitude, etc. That's where the interactions are encoded. So we will be trying to characterize these higher point functions. Okay, this is what we will be interested in. Okay, so I said that the observables of interest are correlation functions, but actually I'm going to be focusing and I will be working with a more primitive object. Okay. And this more primitive object is the wave function of the universe. So what is this wave function of the universe? We call it psi. Okay, this is a functional actually, so it should be called wave functional. And this is a functional of the fields. Here I just write one scalar field, but it could be any number of fields, of course, gravitons, whatever, photons, etc. This is a field profile in this surface in this fixed time surface. Okay, so it's just the field profile at that specific time. So it depends on the spatial coordinates, 3 spatial coordinates. And this wave functional is basically the overlap between the vacuum state and the state corresponding to this field profile on that boundary, on that reheating surface. And this wave functional can be computed in terms of a path integral. So this is the path integral, just the exponential of the action. This phi, this bar phi, is basically the field, the field evolving, which evolves in the inflationary spacetime, subject to the boundary conditions that in the very far past time. So because maybe I should have said it, but if this reheating surface corresponds to conformal time equals 0, then that means that well, we have infinite conformal time towards the past. Okay. So in the very far past, the boundary condition for this field is that it's in the vacuum. Okay. That's where this vacuum comes from. And in conformal time equals 0, the boundary condition is that the field has this profile. Okay. And then this wave functional is basically this path integral, which integrates over all of the possible trajectories of evolution of the field, and is giving us the probability that this field has this specific profile at the end of inflation. Okay, it's basically analogous to the wave function of quantum mechanics, but in this case it's a wave functional because we evaluated on field profiles. So this object, this wave function of the universe, I said that it is more primitive than the correlators because it computes the correlators. Okay. So if I am interested in correlators, correlation functions of well, several copies of this field phi, for example, n copies, whatever. Yeah, this is a correlation function of this field phi at that fixed time surface. Then this is going to be given by this path integral, in which I insert fields and I wake them with the wave function of the universe. Okay, and then this path integral goes over all of the possible profile configurations of the fields in that boundary, and they are weighted by this, which gives us the probability for this field profile, as I said. Okay, so I can compute any correlator if I know this wave function of the universe. So this is the object that we will try to compute. And this wave function of the universe in perturbation theory, we can do the classic move of approximating it using the saddle point approximation and approximating it by the exponential of the classical action. So this classical action is basically the action evaluated at the classical solution for this field phi. So I solve the equations of motion, I find the classical solution, and I plug it in the action, and that is going to give me this wave function of the. Okay. Now with the field profiles, if these field profiles are small, then, oops, this wave function of the universe will take, can be expanded in this way. So this will be a sum, an infinite sum, actually. For some integrals, the momenta. I will now explain a bit better. And these are the fields. Okay, so so first thing you should notice is that we are now working, that I moved to Fourier space, okay? We will actually work in momentum space for the rest of these lectures. We do that for, well, historical reasons, because in cosmology it's common to work in momentum space. Well, actually, it has some advantages, like momentum conservation is very easily formulated in momentum space, etc. So yeah, okay. So what I've done is I have just expanded this wave function of the universe in this kind of series in the fields, okay, in the field profiles. So we will have in principle an infinite number of terms with a growing number of field profiles, and this psi here is the function, some functions of the momenta, which basically are giving us the coefficient for each of these terms in the series expansion. So these psi n are called wave function coefficients. And they basically contain all of the information about this wave function, right? I mean, if you give me all of these wave function coefficients, the infinite wave function coefficients that there are, then I know what this wave function is, okay? So they contain all of that, all of the information. And because they contain all of the information, when we compute these correlators, we can actually express these correlators in terms of these wave function coefficients. They are related in a very simple way. So mathematically, let me be more precise. So, for example, if I am computing a correlator of two of these scalar fields, I just label them with 1 or 2 instead of writing x1, etc. This is going to be given by 1 over 2 times the real part of this wave function coefficient, of the wave function coefficient that corresponds to the term of the series with 2 fields. Okay. And well, if I have 3 fields, then this is going to be proportional to the wave function coefficient of 3 points. Well, I don't want to write it explicitly, but you know, this wave function coefficient will depend on the moment of the 3 fields, and well, there is a normalization here with the 2 point wave function coefficient of all of the fields. This goes from 1 to 3. Okay, so yeah, well, just to finish. If I want to compute a 4-point correlation function of these fields, this will be given by the real part of psi4 and another contribution, which is called disconnected contribution, which is a product of 3-point wave function coefficients. And the dependence is going to be this. They will depend on K1, K2, for example, and the other one will depend on this minus Ki, K3. Sorry. Okay. And then there is again a normalization with this 2-point wave function coefficient. Okay, so of course this goes on, and for any endpoint correlator that you want to compute, you can do it in terms of this. You can express it in terms of these wave function coefficients. So I started by saying that the observables of interest are these correlation functions, but the objects that we will be working with and the objects that we will try to compute, etc., are these wave function coefficients. Okay, and I hope it's clear that they are directly related. Okay, any question? Okay, so
yeah, sorry, Carlos. I think that it's not so direct the fact that you have the 2, the 3, and the 4-point function in terms of this real part. Just looking at the form of psi, I don't know. Can you comment more about it? I mean, how to get the 1/2 real part of psi2 just from the wave function?
Yeah, good. So as I said, this 2-point correlator, okay, is given by this path integral, where here I have to weight it with the with this wave function of the universe squared. Okay. So if you expand this thing here, well, if you substitute this and then expand the exponential, you're gonna get basically something like, sorry, this times a couple of copies of the fields. Actually, the number 2 comes. This number 2 comes from this 2, so you'll have twice this because this has a square, and the real part, the fact that you're picking only the real part of this wave function coefficients, comes from the fact that you are writing the the modulus square. So then the imaginary parts will cancel. This is on top of an exponential, right? So the imaginary parts of these things will cancel when you compute this. So that is why we only pick the real part, twice the real part. So by doing, so you do this, and then from the usual techniques of path integral computation and so on, you derive all of these, all of the different terms. Yeah. So this is how this thing, this relation arises.
Yeah, thank you.
Okay. Yeah. So very good. So we are interested in these wave function coefficients in this size. These objects can be computed by using a diagrammatic expansion, similar to the Feynman diagrams for scattering amplitudes, or similar to the Witten diagrams of ADS, CFT, and so on. So So this size can be computed diagrammatically. And for example, here I have drawn the diagrammatic expansion that we would use to compute a 4-point wave function coefficient, for example. So we'll have to sum over all of the different diagrams that have 4 external legs, right? All of these diagrams will contribute to this wave function coefficient. So we have, for example, this contact diagram, which comes from just this contact interaction in the bulk spacetime. We have this one, which corresponds to a single exchange, tree level. We have also this one, which has a loop, etc. Any diagram you can write with the interactions of your theory. For example, your theory has only 3 point cubic interactions, then you will not have this diagram, for example. Okay, so how do you do this in practice? You have to draw, of course, the diagrams, but then you have to translate them into something mathematical. And the way you do it is by assigning propagators to all of these lines. The lines that end up in the boundary are called bulk to boundary propagators, just like in Witten diagrams. And these other lines are called bulk to bulk propagators. And the propagators come from the classical solution for the field. So basically, our field in the bulk is this. It depends on, well, sorry, let me write it in momentum space. So this is the late time profile of this field. So the profile in the boundary, and this K is the bulk to boundary propagator. Okay, this K kappa, whatever. I hope my handwriting is not too horrible. And the bulk to bulk propagator is this object here, and yeah, and this bulk to bulk propagator is actually the green function of your equation of inhomogeneous equation for this field. Okay, and this bulk to boundary propagator is just the classical solution to the equation of motion. And of course, they have boundary conditions such that this thing works well. So for example, the boundary condition for the bulk to boundary propagator is that when eta goes to 0, so when this propagator goes from the boundary to the boundary, it has to be 1, because at that point the field in the boundary has this profile. And in the same limit, when one of the times goes to 0, so goes to the boundary, this thing has to vanish, this bulk to bulk propagator. Okay, just such that we recover the correct thing, which is this late time profile. So when we have this information, we can then compute these diagrams. And the way we do it, the way we do compute an endpoint function, wave function coefficient, is by summing over all the diagrams, as I said. Diagrams, and these diagrams are computed by integrating the time insertion of every vertex that you have in the diagram. You multiply here with the whatever your coupling constant or whatever power of time or whatever that comes from your vertex. Then you multiply all of the bulk to boundary propagators, and then all of the bulk to bulk propagators. Okay, so basically, usual diagrammatic way of computing observables. Okay, so I wanted to do an example of this just for you to see how it works more explicitly. And the example I want to do is a massless scalar in flat space. So now imagine that we are not in an inflationary spacetime. We are just in flat space, Minkowski spacetime. But we still want to do this, compute the wave function of this universe, and compute correlators at a fixed time slice. For example, t = 0. Okay, so this fixed time slice is going to be t = 0 in this Minkowski spacetime, and we are interested in correlators there. So the first thing that we need to know is what are the propagators for this massless scalar field in flat space, and they are quite simple. At least the back-to-boundary propagator is given just by a plane wave. Well, this k is the modulus of the vector. Okay, and the bulk-to-bulk propagator is a bit more complicated, but it's simply given by this expression. Okay. So this bulk-to-bulk propagator is this object. This second term is just the same as the first term, but with the 2 times interchange. It is symmetric in the 2 times, and then this term is here to ensure that the boundary condition at t going to 0 is satisfied. Okay, so we can then try to compute, for example, a 3-point wave function coefficient. I have labeled here the 3 legs. So this one has energy k1, energy k2, and energy k3. These energies are the modulus, the moduli of the momenta. And then this is computed in the following way. So we have this I, which is just comes just from the vertex, from the only vertex that we have here. We have an integral on time, and we have to integrate from the very far past to this time boundary. And then we have a product of the 3 bulk to boundary propagators, right? Yeah, and if we substitute, we just have this. We're actually going to call this sum of all of the energies big K. Well, hope it's clear. This is a big K. This is the sum of the 3 energies of the involved in this process, in this diagram. And now we can do this integral. The result is this. We have to evaluate it at the two limits. So yeah, the first one will just give us this, and then the second, the other limit, the far past limit, is a bit more subtle because, as you can see, it has an oscillation. But the point is that here we have to use a mathematical trick that helps us project our state onto the interacting vacuum. The fact that we have this oscillation comes from the fact that we want to compute the overlap of some field profiles with the interacting vacuum, but this oscillation is telling us that there is some how to say, some interaction, some interaction between the non-interacting vacuum and the state with 3 fields, and in order to project over the actual interacting vacuum, which is a a linear combination of them, we have to use this I epsilon prescription here. This I epsilon prescription is ensuring that we pick the right vacuum, and is also regulating the integral in such a way that, you know, if you substitute this here, you can see that this exponential picks a tiny real part, and then the time going to minus infinity makes it vanish. So the final result is just this. This 3-point wave function coefficient is just 1 over the sum of the 3 energies. And, you know, first thing you should notice here is that the sum of the energies involved in the process is not 0. Otherwise, this would be infinity. This would make no sense. And this is one of the big difference between scattering amplitudes and these objects, which are which are basically correlation functions or wave function coefficients at a given fixed time. So we are picking a time slice. Okay, this means that we are breaking the time translation symmetry of the problem, and that is why we are losing energy conservation. Okay, so the sum of the energies is not 0, like scattering amplitudes. Okay, this was the 3.1. It was very easy. We can try to do the 4.1. In this case, we will have 2 vertices. So we have to integrate over the 2 time insertions, left and right. And then we will have these 2 back to boundary propagators, which will give me this TL, and then the other 2 legs will give me this T right, and then, well, we'll have bulk to bulk propagator from T left to T right. I have defined here, well, S vector as the sum of K1 and K2 vectors, and then the modulus of that, so the energy of this internal line is small s. Okay, and this bulk to bulk propagator will depend on that small s. Okay, so this bulk to bulk propagator has basically 3 terms. So I'm going to divide this integral in 3 parts. And the first one, let me actually copy all of this. So the first term is this T left minus T right times see. Yeah, actually, let me do T right minus T left, and then this is T left minus T right. I just picked this first term of the bulk to bulk propagator. Okay. So this step function implies that one of the integrals is not going to run from minus infinity to 0. So the left integral is going to be this K1, 2. Let me write K1, 2, meaning K1 plus K2. Okay. Minus S times T left. This minus S comes from here. Yeah, and then we have the other integral, which will run from minus infinity to T left. Okay. This is a consequence of this step function. Okay. And let me call this sum of energies E right. Okay. Energy right. The reason why I'm calling it energy right is because it's the sum of energies that enter in the right vertex. It's K3 plus K4 plus S. So I'm calling it E, right? Okay, so we can do this integral, and the result that we're gonna get, we also have to take into account projecting into the right vacuum and so on. And the result is going to be, where is it? Yeah. This. Oh, with T left. And we will also have energy, right? And well, we can combine these two. We're going to have a sum of all of the 4 energies in this exponential. Sorry. Now we can do this this integral. By the way, this sum of the 4 energies is the total energy of the external legs, and I'm gonna call it E. Yeah, and when you do this integral in the same way, you get this result. The 2s is coming from here. The 1 over ER is coming from this one, and the 1 over E is coming from the integral of the exponent. Okay, so we have the first part of this wave function coefficient. The second part is actually the same, but just exchanging T left and T right. So the result is 2s E left. Okay. And the third integral is the one associated to this term. Integral is actually this one. In this case, we don't have a step function, so we don't mix integration variables, and we just have E left and E right in each of the 2 integrals. So in this case, the result is this: E left, E right. Okay, so we have the 3 parts, and now this wave function coefficient, sorry, 4-point wave function coefficient is the sum of the 3 of them. So I can, well, so basically you just have to sum this, and you will see very easily that this is 1 over E left, E right. So the result for this process, for a massless scalar in flat space, is that the wave function coefficient is 1 over the total energy of the process, the sum of the 4 energies, times the energy that enters in the left vertex times the energy that enters in the right vertex. And none of these are 0 because we don't have energy conservation. Very good. So is there any question about this example? Okay, so this was a very simple case. It was a massless scalar in Minkowski, but and you could see that the propagators were very simple. But for example, for a massive scalar, I'm not even talking about spinning particles. There's a massive scalar in the sitter, which is a spacetime that we will be interested in. The back to boundary propagator takes this form. So this eta star is the location of the boundary. This H is a Hankel function of the second kind, and this nu here, let me write it explicitly, is well, it's just a number related to the mass of the field. It's given by this expression. H is the Hubble constant. So you can see that this back-to-boundary propagator is very, very complicated. It's a Hankel function, so it has a complicated analytic structure. And well, the bulk-to-bulk propagator is even worse. Don't know if I should write it explicitly, but well, it's basically. Sorry. It's basically also a combination of Hankel functions of the first and the second kind. Like this. Also with some step functions here. Same, but exchanging the times. And then another. Okay, so this is other product of Hankel functions. So this propagator is also very, very complicated in general, right? And the integrals that these propagators are going to give rise to, if we try to compute these wave function coefficients, are going to be very, very complicated in general. And they will have all kind of funny things, branch cuts, etc. Very complicated structure. So it's not possible in general to compute these wave function coefficients unless they are, the most simple cases. So very complicated. We need, or we would like to have, some other method. Some other method to compute these wave function coefficients. Okay, so this takes me to the second part of the lectures. Is there any question at this point? Okay, if not, yeah. Now I'm starting the second part, which is about trying to explain what a bootstrap is, and why is it interesting to do a bootstrap of cosmological correlator, or actually cosmological wave function coefficients. Okay. So, in field theory, the usual way to compute things, the classical way to compute things, is to start from some principles, and these principles are well, usually the very cherished principles of locality, unitarity, causality. These are principles that we assume for most of our of the theories that we write, and then some set of symmetries that depends on what we are, which specific model or theory we're writing. So we start from those principles that our theory needs to satisfy, and then we write a Lagrangian, make a Lagrangian formulation of that theory. We write a Lagrangian that satisfies all of those principles. So a local Lagrangian, which is invariant under the symmetries, etc., etc. And then from this Lagrangian, we derive the equations of motion. We'll write some Feynman diagrams, or Witten diagrams, wherever, depending on the situation. And we study the evolution of the fields, and in that way we compute the observables, which are correlation functions or scattering amplitudes or whatever. So this is the usual way. The bootstrap philosophy is about skipping this intermediate step and going directly from the first principles to the observables. So this is bootstrap. And in this way, what we do is, we skip all of these intermediate steps, which usually involve non-physical degrees of freedom, gauge redundancies, and things that do not have physical meaning by themselves. And we go directly from the physical principles to the actual objects that we want to that have a physical meaning, an observable meaning. Okay, so this is the bootstrap. Yeah, sorry. Okay, so this is basically the bootstrap philosophy in a nutshell. And I want to tell you about the successful story, a successful application of this bootstrap philosophy, which is the application of the bootstrap philosophy to the S matrix. Okay. So to the computation of scattering amplitudes. So let me start with an example, which in principle is a bit complicated. So for example, consider gluons, okay, at 3 level. So scattering amplitudes of several gluons at 3 levels. So for example, 5 gluons. This one here. Here we can have any kind of 3-level process between them. So this has a 3-level 25 Feynman diagrams. Okay. If you want to compute this process, you, in principle, according to the usual way of doing things, you have to compute the 25 Feynman diagrams. It's doable, but it's going to be boring for sure. And when you compute them, you add them up. It's going to be a very large expression, but you will find some simplifications, some redundancies, then some things that add to 0, etc. And in the end, the result is going to be the following. So your amplitude, if you take all of the gluons to have the same helicity, is going to be 0. So all of these 25 very big expressions with all kind of propagators, 3-level processes, they will add up to 0. If you take one of the gluons to have a different helicity, for example, minus helicity, and all of the rest have plus helicity, the result is still 0. It's only when you take 2 gluons to have different helicities that the result is non-zero. And the result is actually very simple. It can be written in just this space. It's going to be this. Where these brackets are spinor helicity variables. I don't know if you're familiar with them, but basically they encode the information about the momenta and the helicity of the gluons. Okay, so in terms of these very useful variables, spinor helicity variables, the amplitude is just this after summing over 25 Feynman diagrams. For the case of 6 gluons, you have 220 Feynman diagrams. And again, this is doable, but very, very, very boring. And the result is the same. If you take all of the gluons to have the same helicity, it's 0. If you take all of the gluons but 1 to have the same helicity, it's 0. And you need to take 2 gluons to have a different helicity for it to be non-zero. And the result is basically the obvious extrapolation of the above formula to 6 points. Okay, and this is general. You can add as many gluons as you want. The result is always going to be 0 for all equal helicities and all equal helicities but 1, and for all equal helicities but 2, it's called the maximal helicity violating case. The result will be given by this very compact expression, which generalizes in the obvious way. So this is a huge simplification, right? This formula is called the Park-Taylor formula. It's due to Park and Taylor. In the 85. And it was originally guessed because they saw that, for the simplest cases, the thing was simplifying a lot. So then they guessed that that it was a general formula. And then some time later, it was bootstrap from first principles, just from locality, unitarity, Lorentz invariance, and so on. People were able to argue that this is the only consistent answer, and that these are the only consistent answers too. So this is a successful story of how the bootstrap can take you from a huge number of Feynman diagrams that you really don't want to compute to the actual very simple answers without going through the pain of computing the diagrams. And
I have just a question, Carlos. Sorry.
Yeah.
For the 6-point case, you don't have as well the 3 minus and 3 plus, right?
You mean, yes, sure. So you also have this case, but that case the formula is not so simple, sadly. So yeah, this is also non-zero, but the formula is different. It's not given by this Park-Taylor formula. This Park-Taylor formula is for the case of 2 different helicities.
Oh, but probably, okay, the question is this a question for the amplitude when you have 3 minus and 3 plus, for instance? The same for the 7-point case when you are considering 3 minus and all the other plus. It's like universal properties of this amplitude. You
mean, yeah, if, I don't know about that in particular. Yeah. I don't know. So you're asking if I take 3 different ones and all the rest the same, if there is
the
some
same
structure
for all type. Yes, exactly.
I don't know. Yeah. Okay. Yeah. So this was just a very concrete example for you to see the power of this. But let me be a bit more. Let me go a bit more to the basics. So we have a 3-point amplitude. Okay. You don't need to compute all of the diagrams that give rise to this amplitude. All of these amplitudes, every 3-point amplitude is totally fixed by Poincare invariance. So if you were very naive, you would start computing diagrams until you get tired. But the bootstrap philosophy tells you that you don't need to. That actually only Poincare invariance is powerful enough to fix the form, the analytic form of these amplitudes. For 4-point amplitudes, of course, the story is a bit more complicated, but they are still well, the analytic structure is fixed at tree level, and it's very well characterized at loop level as well. So for the 4-point amplitude at tree level, there are several things you can use. So one is Lorentz invariance, of course. The other one is locality, and another one is unitarity. And the combined power of these these three principles restricts the shape of the amplitude. So more concretely, Lorentz invariance. It implies that the scattering amplitude can only depend on the Mandelstam variables, right? ST and U, and actually one of them is not independent from the others. So S and T. Locality. You can show from locality that that 4-point amplitudes at 3 level, the only kind of poles or singular points that they can have are simple poles, and that they are related to particle exchange. So they can only have simple poles from particle exchange, so from virtual particles inside this diagram. And from unitarity, you can show that the coefficient of the coefficient of these simple poles has to be positive. Okay, and actually by combining locality and unitarity, you can also show a very powerful thing, which is that in the limit in which in which an internal particle goes on shell. Yeah, so for example, imagine an exchange diagram, and we take the Mandelstam variable S to m squared, where m is the mass of the particle that is being interchanged. This amplitude has to have the simple pole that I already mentioned, and the residue has to be a factorization of the 3-point amplitudes that you have in each of the vertices. Okay. So let me put colors, because more mathematically, all of this means that the 4-point amplitude at 3 level, it depends on Mandelstam variables, and this is given by Lorentz invariance. It is going to be, well, it's going to, okay, let me start with exchange actually. We have the condition of locality, that that this amplitude needs to have a simple poles corresponding to particle exchange, and the coefficient has to be positive by unitarity. And we know what is the coefficient of these simple poles, because we have this condition. And the coefficient has to be a Legendre polynomial of order S, where S is actually big S, is the spin of the particle that is being interchanged, and M is the mass. And then, well, you will have some other, you have the freedom here to add a polynomial of the S and T variables. And then you have to also sum over the T channel and the U channel, because this one here, this pole here corresponds to the S channel exchange, right? So let me draw. This term here corresponds to this kind of diagram, to this S channel exchange of a particle with mass M and spin S. And this other term here, this expansion, corresponds to the EFT expansion, basically. So to contact terms and so on. And these A's are just coefficients that are given by the couplings of your Lagrange. And then you sum also over the T and U channel, of course. Okay, so yeah, so these are the conditions for 4-point amplitude at 3 level. As you can see, these Lorentz invariance, locality, and unitarity are very powerful. And these this fact that the amplitude has to factorize when the internal particles go on shell is very, very powerful. It's very, very restrictive. And for example, if you consider only massless fields, it restricts very much the kind of theories that you could have. You could try to, for example, formulate a theory for massless spin 2 coupled to massless scalars, and you will discover by requiring this, you will discover that the only consistent thing that you can write involves the equivalence principle. So it involves that all of the matter couples with the same strength to the graviton. Or for example, if you try to write gauge theory, spin 1, coupled to matter as well, you will find that the only consistent thing that you can write is if there is charge conservation, for example, etc. So this condition is very powerful, and it tells you that there is only a small menu of possibilities for which kind of theories you can write for massless particles. So this is the power of the bootstrap in the case of the S matrix. But let's go back to our observables of interest, to these correlators. So, you know, I said before that these correlators encode information about the processes, quantum mechanics of inflation. Again, this is formal time, and this surface is the surface of zero conformal time. This fixed time surface. And you know, the observables are just these correlators or wave function coefficients that live on the boundary, and they only depend on they do not depend on time, right? They are correlators at the boundary. They just depend on the three-dimensional spatial momenta of the different insertions. So this means that the time evolution here in the bulk during inflation is integrated out in the final observables. It's not there explicitly as a time dependence, but it is integrated out. Okay, and these observables are the only observable. These correlators, sorry, are the only observable output of the inflationary process, because we cannot access inflation directly or observationally. The only observational access we have is to these correlators in the boundary. So if these correlators are the only observable output and they have time evolution integrated out in them, why can't we just try to fix them, try to understand them at the level of this boundary without making explicit reference to the time evolution, right? Without you know, solving the classical equation of motion, propagators, diagrams, etc. So this is the aim, the goal of the cosmological bootstrap, to forget about time evolution equations here in the bulk, and instead focus focus here in the boundary, impose first principles here. So impose locality, unitarity, symmetries directly on the boundary. And the advantages, well, as I probably transmitted you already, the advantages are mainly two. One is that the calculations will be more simple in general. Maybe not in all of the cases, but generically, it will be more simple. And the other more conceptual, not so instrumental, but more conceptual advantage is that we directly focus on the observables. And we get rid of all of the redundancies and non-physical avatars related to for example, to the usual time evolution calculation, Gauge degrees of freedom, things like that. Okay, so this is basically the cosmological bootstrap. Yeah, and well, I already told you that it is nice to try to understand these correlators because inflation was very energetic, and we can kind of do collider physics with it, but very energetic collider physics. And here I just wanted to make this a bit more precise. So correlators from exchange of a massive particle, okay, show oscillations, okay, in certain limits of the momenta. So when you take the distribution of the points of your correlator, the distribution of the insertions, when you take them to a certain limit, when you do a certain shape, the correlation function shows some oscillations. So this is the cosmological collider case. And these oscillations that you can see here, well, the frequency is related to the mass of the field. So in a way, we are doing spectroscopy in a similar way as people do in the particle colliders, right? In the particle colliders, you measure the number of events that you see for a given center of mass energy of the process. And when you see a peak, that means that there is a resonance there. And the resonance is located when the center of mass energy is equal to the mass square of your process, right? Just from the poles that we saw for scattering amplitudes. So this is the analog in the cosmological case. You will see these correlations oscillating in this limit with a frequency that will tell you the mass. In a similar way, by studying the angles between the momenta of your observable, you can also find out what the spin of the particle is. So it's basically you can do spectroscopy. So okay, so I hope this was motivating, and this kind of explained why we want to bootstrap these cosmological correlators. Okay, is there any question here?
Yeah, probably is a stupid question, but what happens when you don't have a mass? So you have some oscillating massless particles or whatever?
Yeah, when you have a massless particle, we're going to actually study that case in these lectures. We're actually not going to see the massive case. When you have a massless exchange, for example, in general, you will have correlators which are meromorphic functions of the momenta. So they only have simple poles. They don't have all of this rich analytic structure with oscillations and cuts, and etc. They will be simpler functions, which in general will be meromorphic. So yeah, in terms of accessing the analytic structure, well, in terms of accessing these oscillations and so on, they will not be here, but they will not be there. But yeah, but you can also compute the correlators in that case. And actually, we're going to focus on those, on the ones that involve massless particles and only involve poles. Okay, any other question? Okay, if not, I will start in the remaining time with the third part, which is actually the more technical part, which is about the different techniques and methods that we have developed, we and others have developed to bootstrap cosmological correlators. And this section I have divided in several subsections, which refer to the different methods or tools or things that you can use in order to bootstrap cosmology. So the first one is about the symmetries, how you can use the symmetries to obtain these wave function coefficients. Then I will talk about the singularities that these objects have, word identities related to gauge invariance, unitarity of the bulk and how it translates into the boundary observables, some energy deformations that we use to compute them, and then other methods. So I don't know if I will have time for everything, but I will try. Okay, so let's start with the symmetries. So inflation took place in an approximately de Sitter spacetime. Okay. Let me write it. And we can kind of quantify more or less how close to de Sitter was the inflationary spacetime. Well, at least there is a more or less a way in which we can quantify this. So as you know, maybe de Sitter spacetime has a scaling invariance, and the 2-point function of a scalar perturbation, massless scalar perturbation in de Sitter would be scale invariant. But we have measured this 2-point function for our universe, for the actual inflation. And we have measured that it is proportional to 1/k. K is the momenta of the fluctuation to this power. And the deviation from scale invariance is given by this 1 minus ns. So scale invariance would correspond to k cubed. So 1 minus ns tells you what is the deviation from that scale invariance. And we know that for our early universe, for our inflation, this deviation from scale invariance is this very small number. So in other words, you know, if ns equals 1, then you have exact scale invariance, and ns in our universe equals 0.96. So it's very close to 1. So in this way, we can we can make the argument that the inflationary spacetime is well approximated by a de Sitter spacetime. So when we study our inflationary spacetime, we assume that we have some de Sitter here or almost de Sitter. Well, we can leverage the symmetries of de Sitter to try to say something about the correlators from inflation. And the de Sitter isometries, when you go to the boundary that we are interested in, so when you take eta to 0, when you take the limit, you realize that the de Sitter isometries become the symmetries of a 3-dimensional, because the boundary is space-like 3-dimensional, Euclidean CFT. So the de Sitter isometries become the symmetries of a CFT in the boundary. Okay, so here I have the isometries. Here I have the conformal symmetries. And I'm saying that when eta goes to 0, they map to each other. So spatial translations is an isometry of de Sitter, and when you take eta to 0, well, they are actually the same. They are actually spatial translations also in the boundary, because they are just a symmetry of the spatial direction, so they don't change because you take a specific limit of time. So they are the same. Same thing happens for rotation. Well, sorry, let me write this expression. So rotations in the three-dimensional spatial directions, they become also rotations in the boundary, and then dilatations in the bulk de Sitter. So the isometry of de Sitter becomes just the scaling symmetry of a conformal field theory in the boundary, and de Sitter boosts they become the special conformal transformation in the boundary, SCT. So this is how the Sitter isometries map to symmetries of a CFT. I'm not saying that there is a CFT in the boundary for every theory in the Sitter, as one would say for ABS-CFT, etc. Well, this has been conjectured some time ago, but it has not been proved. We are not sure that is the case. But the point is that the isometries of the Sitter do coincide with the symmetries of a CFT in the boundary. Okay, so this in particular, this implies that these objects that we like satisfy these symmetries. They satisfy the symmetries of a three-dimensional Euclidean CFT. Okay. So we can write them as correlators which satisfy this conformal symmetry, and this implies that, well, I can extract a delta function of momentum conservation here. So this delta function of momentum conservation just comes from translation invariance, and it's going to be there for all of the wave function coefficients just because of translation invariance. So I'm going to basically forget about it, and I will mainly work with this prime conformal correlator, which is the correlator with the delta function stripped off. Okay, so that's what the prime means here. Okay, so these wave function coefficients have the symmetries of CFT correlators, and one could wonder, well, what are these fields in these CFT correlators that these wave function coefficients are equal to? So these O's, these fields here, are actually primaries of a CFT. They have the symmetry properties of primaries, and we will call them dual fields to the actual fields that we have in the Sitter, just in the spirit of ABS-CFT and so on. And their scaling dimension is delta plus this for scalar fields. So spin equals 0. And for spinning fields, this is the formula. So what I mean is, if I'm computing the wave function coefficient that corresponds to a given set of fields in the bulk de Sitter, so the wave function coefficient that multiplies a given set of fields in the wave functional of the universe, in that expansion that I talked about before. These fields here of the putative conformal field theory are going to be dual fields to those fields in the sitter, and their scaling dimension is going to be given by the mass and the spin of the fields in the sitter, of the corresponding dual fields of the sitter. So for example, for a massless field in the sitter, we're going to have that the scaling dimension of the dual field is 3. Okay, so well, remember that these wave function coefficients were giving me the correlators of the sitter fields in the boundary. So if I am interested in the correlator of 2 scalar fields, for example, sigma, remember that I had 2 times the real part of this. Well, now I can say that this is twice the real part of this. Oops. Of this correlator of conformal primaries with scaling dimension given by this formula. And well, similarly for, well, let me do a more complicated case, but imagine that I want to compute a correlation function of tensor fluctuation and 2 scalar fluctuations in the sitter. I'm calling the scalars sigma. Then this will be given by the formula that we already saw. But now I am substituting I'm writing the wave function coefficients as correlators of a CFT. And then the dual field of the tensor fluctuation is going to be the stress energy tensor of the CFT. Is going to have the same structure and properties of the stress energy tensor. And then we have to normalize. Okay, so yeah, so this is a very important constraint on the structure of this size, right? It's telling us that it satisfies a certain set of symmetries which we can use to constrain them. So to be a bit more precise here, well, I will do probably an example, but
sorry, Carlos, I have just a question. Sorry if I interrupt you. If we consider the scaling dimension that you have written, I mean, it's strange that the massless case, when you don't have any spin, so for the L equals 0, and in the massless case, you have a scalar field, the dual a scalar operator that has scaling dimension 3. And this is the exact the case where you're considering a stress energy tensor, like an operator. So, for instance, if you take L equal 2, but massless, you have the same delta.
Exactly. Yes.
So, but I mean, this is confusing to me because what is the difference now about the 2 type of operators? Just the spin part that you will have in your correlator.
Exactly. Yeah.
Okay.
Yeah. Exactly. Yes.
Just that one. Okay. I see.
Mm-hmm. Yeah, the dual operator to the tensor will be also a tensor. Yes.
Okay.
Okay. So I think my pen is out of battery. Okay, let me ask while it charges. Any other question at this point? Ah, it works. Okay. Yeah. So these wave function coefficients satisfy the symmetries of CFT. They satisfy conformal symmetries. What does it mean to them? Well, we already saw that the translation invariance means that they come with a delta function of momentum conservation. So what do the other symmetries imply? So what the other symmetries imply, for example, is that this, which in general depends on the momentum vectors, it will only depend on doesn't work. I think my pen is tired. Give me a second. Okay. Okay, work again. Yeah, so rotation invariance implies that this wave function coefficient will depend only on the momentum, on the moduli of the momenta, and on contractions of the momenta, right? So only rotationally invariant quantities. Scaling symmetry has implies a conformal word identity, so a differential operator, a differential equation that these wave function coefficients need to satisfy, right? So it implies this. This is the differential equation, and then special conformal transformations imply a more complicated, actually, differential equation, where we sum over all of them. Well, I don't know if it's worth writing the whole thing, but this is the classical conformal word identities for conformal correlators. Okay. Okay. So these are restrictions on our wave function coefficients. So we could use them to bootstrap them, right? So I wanted to do the example of a 2-point function of scalars. It's basically doing this conformal bootstrap classical thing of fixing the 2-point function of a scalar just with this symmetry. But I don't think I have time because I want to end this part today in the remaining 10 minutes. So I will skip this, but this is just the typical story that what I wanted to say is just the typical story that this 2-point function in a CFT is totally fixed by the symmetries, right? And it is actually proportional to a delta function of the scaling symmetries. This comes from special conformal transformations times a delta function of momentum conservation as well from translation invariance times this power of the momentum of the modulus of the momentum, and this is given by the scaling symmetry times a constant. Okay, so the only free parameter is in this 2-point function is the constant. So this is a well-known fact. I wanted to derive this a bit more detail, but I think probably many of you already know this. Yeah, so we have all of these equations that I just wrote. This is just the same but more beautifully written. So one strategy to try to bootstrap these wave function coefficients is to try and solve these differential equations, right? So find solutions to these differential equations for the 3-point case, 4-point case, etc. So this is what part of this cosmological bootstrap has been about for some years, and this was the main strategy that we pursued on these papers. Well, we in these two papers and they in this previous paper. So you can find a lot about this in those papers, and you can also find a lot about this strategy in these lectures that Daniel and Guy have given. So these are some lectures that Daniel gave in Lecce a couple of years ago. These are some other lectures that he gave in Taiwan, and these are some lectures by Guy in GGI actually, the beginning of 2020, I think. And in those lectures about the cosmological bootstrap, they focus on this method of finding solutions to these differential equations. So basically using very heavily the symmetries of the boundary to bootstrap these observables, this quantity. In these lectures, however, I wanted to do something complementary, so I wanted to avoid repeating the same things. So we will instead focus on other methods, which are particularly powerful for meromorphic wave function coefficients, as I mentioned before. So let me write it. We will focus on other. Meromorphic. So basically rational wave function coefficient. And this, well, so this means that tomorrow I will show you methods to bootstrap these wave function coefficients when they are rational, which do not rely so much on the symmetries, on these conformal symmetries, but try to use some other principles. So yeah, that's what we will do tomorrow, starting with the singularities.